We are going to continue with the next chapter, which is going to be discussing basic concepts of bonding. As you recall from the previous chapters, we went over what valence electrons were. And valence electrons are pretty much the electrons on the outermost shells. For example, this will contain 2 valence electrons. We have a scientist that developed this idea that valence electrons we're going to be represented with dots. As you can see, your group 1 has 1 valence electron, your group 2 has 2 valence electrons, 3A, and so on. The group 8 has 8 valence electrons, with the exception of helium, who only has 2 valence electrons. Then we have a scientist, like I mentioned, he's an American scientist who developed this idea that we were going to represent valence electrons using dots, and we are going to track those electrons during bonding. So as you can see here, we have aluminum, which has 3 valence electrons, and we want to make sure that we spread that electrons as much as possible. You want to make sure that you put them far apart from each other, and you only are going to be able to put 2 electrons on each side. So 2 electrons top, 2 electrons bottom, 2 electrons right, and 2 electrons left. Not more than that. We also have this idea of the octet rule, and this idea is pretty much, as you know, electrons tend to add or tend to release electrons. They can take in, gain, or lose electrons, or they're able to share electrons. Now, the reason for doing that is because they want to have what is called the octet rule. They want to have 8 electrons on the outermost shell. When they do that, they become like the nearest noble gas. For example, sodium, when sodium loses an electron, this is how we will represent if you're given the electron configuration, that will be your valence electron. So here's, notice the trend, as you go, you're adding 1 valence electrons. What I was going to mention is, for example, if we have sodium, and if we have sodium that loses 1 electron, what's going to happen is that the electron configuration now, it's going to be 1s2, 2s2, 2p6. So that when we say it has an octet, a full octet, that means that the s and the p orbital are full, as you can see here. Now, on a different subject, we're going to start discussing ionic bonding. We're going to go over 3 different types of bondings, and you guys are familiar with this, but we're going to go into more details. We're going to discuss ionic bonding, which is when bonding occurs between a positive and a negative charge. There's an electrostatic attraction. We have covalent bonding when we are sharing electrons, and we're going to have metallic bonding, which is pretty much a pool of electrons. We're going to start discussing ionic bonding. So ionic bonding is pretty much when you have a metal transfer an electron to a non-metal, with the exception of your noble gases. Remember, your noble gases are inert, so they're not going to be able to take in or donate electrons. They are happy the way they are. They are very exothermic. They are very exothermic. So for example, if we have sodium here, and you have 1 chlorine, it's going to give you sodium chloride, and this is the enthalpy. It's going to be very exothermic. Delta H is going to be an exothermic number. Now the question is, where does this energy come from? Where does this energy come from? Keep in mind that in this case, in ionic compounds, one of the elements is going to easily give up an electron. In this case, the metals have low ionization energy. Another element is going to easily gain an electron. This is going to be the non-metal, which has high affinity. The arrow is indicating that the transfer is always going to happen from the metal to the non-metal, from the metal to the non-metal. These are just some features of ionic substances. They are brittle, they have high melting point, they are crystalline like salt. Sodium chloride is like crystalline, and they have very smooth arrangements, which you won't know it until you actually see it under the microscope. Now, there is, as you know, this is an exothermic process, right? So enthalpy is going to be very negative. What factors are contributing to this energy that is being released? In order for us to form sodium chloride, we need to make sure that our sodium goes from Nag gas to Na plus gas. Now, this is an endothermic process. As you recall, this is an endothermic process, and it's pretty much this, and it takes roughly about, I think it's 349. That's how much energy it takes. But then at the end, you actually release, you are going to release less. I think you release 496. So where does this extra energy comes from? That energy that is, this extra energy that is being released. And this energy is going to come from what is called lattice energy. And that lattice energy is the energy required to separate one molecule of solid into a gas. So when you have this process, there's actually extra energy that is being released. Now, the whole process of finding this energy, so at the end you end up with energy of formation, it's through the Bohr-Haber cycle. However, we're not going to be really doing the cycle, and believe me, you should thank me that you're not doing that. But in generally, what I want to just mention is the definition of lattice energy and the trend. So that's what we're going to be focusing on, is the trends. You want to remember a couple of things, that when you are making ions, basically you're going to have to, when you're making something like an ion, like sodium chloride, you're going to have ionization energy involved and electron affinity involved. What you want to remember, that it takes energy to convert the elements to atoms. So for example, if you have a sodium chloride and you want to convert it into different ions, that is going to be an endothermic process, and it takes energy to create a cation. Energy is released when making an anion. So this is back from the last chapter. The formation of a solid releases huge amount of energy, which is an exothermic, which means the formation of salts are exothermic, because in generally you're going to have more energy being released. Notice here we have, you're taking the ion and you're dissociating it into cations and anions. Therefore, the lattice energy, when you go from solid to gases, that is the lattice energy. It's taking in solid and converting it to gases. That's the energy that is going to be called lattice energy, a solid ionic compound into its gas ions. Now this, the amount of energy is released, which means that it's going to be, to make the ionic compound, is through the Bohr-Haber cycle, which we're not going to be doing. We're not going to be touching on the Bohr-Haber cycle, but it's pretty much how you end up calculating the energy. In your book, you have a table with different lattice energy, where you can, if needed, you can use it and you can calculate. You're not going to be using that. What I want you to know is how are you going to, how is the lattice energy going to determine, help us understand which compound will have a higher melting point or boiling point. Before we get into that, there are some trends in the periodic table that you should become familiar with, strengths on the lattice energy. Increasing the charge of the ions. So when you increase the charge, notice what happened with the lattice energy. Notice what happens with the cations. Are you increasing the cations? So notice that here lithium is +1 and cesium is +2. Notice what happens with the increasing the cation radius. Notice what happened to the lattice energy. Increasing the anion radius, notice what happens to the lattice energy. The lattice energy decreases. Now, don't worry about this equation. We're not going to be using that equation to do some calculations, but there are some trends. So let's go over the trends that you need to know. The larger the ion, the weaker the attraction, okay? So if you have two large ions, they're going to have weaker attraction, and it makes sense because if you think about it, here is the nucleus. So this distance is greater. It's gonna be a weaker attraction, right? Weaker the attraction, the smaller the lattice energy, kind of like what we said earlier. Weaker the attraction, so if you have two compounds such as NaF versus NaI, keep in mind that I is a bigger atom. So they're going to have a weaker attraction. Because they have a weaker attraction, that means that they're going to have a smaller lattice energy. And F is kind of smaller, so they have a stronger attraction. Therefore, they're going to have a stronger lattice energy. Here we have some examples. Notice you have here the distance is 241 pm. Here this one picometers, and here the distance is 348 picometers. There is a larger difference. CS was +1, sorry about that. So there's a larger difference, which means there is a weaker attraction. So therefore the lattice energy is going to be less. This has more lattice energy. So here you see how, and it's gonna be negative. It's an lattice energy is going to be negative. So now let's look at other point of view. And this one has to do with the charges. This one has to do with the charges. If we look at the trends in the charge, the larger the charge, the stronger the attraction. The stronger the attraction, the larger the lattice energy. So here we have two where notice that the distance is similar. So the distance doesn't count in a row with this. But notice that this is +1, -1, this is +2, -2. So this is going to have more lattice energy. Now, how would I ask you a question on the exam? I will ask you something like this, and it's not fine. Order the following ionic compound in order of increasing magnitude of lattice energy. So the first thing you wanna do is you wanna make sure you separate them into two groups. You wanna examine them and you wanna separate them into two groups. Notice that this will be one group because they all have +1, and these ones will have another group. The one in green is automatically going to have more lattice energy because they have bigger charges. So this group will automatically be bigger. Now, between these two, which one you want to look at it. These both have oxygen, so obviously that's not gonna play a role, but you want to make sure that you look at your strontium and calcium. Calcium is smaller, which means that it's gonna be closer to oxygen. Strontium is bigger, so it's gonna be further from oxygen. So therefore, calcium oxide should be first, followed by strontium oxide. Same thing, same idea with here. Chlorine is going to be smaller than bromine. So this should be your third and this should be your fourth. And here is your final order. I'm gonna give you another practice and try to do it by yourself. Here's your answer. Here's another practice. Just try to do it by yourself. Make sure you guys understand it. Don't just try to answer it. We can go over this later, but make sure you understand it. Here's the answer. Okay. Moving forward, when we write the electron configuration of ions, notice that what is happening, most metals are going to lose electrons in order to gain an electron configuration to the nearest noble gas. Non-metals are going to gain electrons in order to gain an electron configuration of the noble gas. Transition metals do not follow these rules. They're not going to try to do that. Transition metals lose the valence electrons first, then lose the d orbital electrons for a given ion. So the big picture, transition metals have their own rules. They don't follow the same rules as the other metals and non-metals. Now, a lot of the chemicals that we actually have, they're actually take place between two non-metals. So that's the majority of chemicals that we have. They don't follow the ionic characteristics because we don't always have a metal and a non-metal. So they're gonna fall under covalent bonding, which means that what they're doing is they are sharing electrons, and there's still some electrostatic attraction. There's going to be an attraction between the electrons and the nuclei. There's going to be repulsion between electrons and repulsion between the nuclei. So there is some type of attraction between charges. It's not just going to be as strong as like the ionic compound when you have a metal and a non-metal. For here, what we're going to start notice that we're going to start looking at the Lewis-Dot structures, and we're going to start seeing how covalent compounds, how molecular compounds have a covalent bond. And what they are doing is that they are sharing those valence electrons. And remember that we're going to be representing those valence electrons by showing one dot. The way we're going to start drawing these structures is by remembering how many valence electrons they have. For example, we have hydrogen. Hydrogen carries one valence electrons. Now, this hydrogen carries one valence electrons. When we are sharing them, now this hydrogen has two valence electrons. This hydrogen has two valence electrons, which is happy. Why? Because hydrogen likes to follow what's called the duet rule, meaning it likes to have two electrons. It likes to be surrounded by two electrons. Chlorine, on the other hand, it has 7 electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Notice that when it's sharing that electron, now this electron on your left has 8 valence electrons, and this electron on your right has a valence electron, which follows the octet rule and is happy. Sometimes the electrons that are being shared, and it's a preferred way, it's being represented by a line, which represent the electrons are bonding. So these are called bonding electrons, bonding pair. Bonding pair of electrons. We also have electrons. So notice here, we have fluorine and hydrogen. There is an electron that is being shared. The electron of hydrogen is being shared with the electron of fluorine. And now fluorine has 8 and hydrogen has 2. So in order to, fluorine got the octet rule nearest to the noble gas. And in the hydrogen, notice that is like sharing that electron in order to compete. So oxygen has 8 electrons here, nitrogen has 8 electrons, carbon has 8 surrounded by La electrons. Each bond represents 2 electrons. There are some terminology that I want to go over to make sure you guys understand. This pair of electrons that are going to be converted to a bond is considered bonding pair. Bonding pair. These 2 electrons that are left are called lone pair, or also called non-bonding pair. And it's important that you know your terminology because we're going to be referring to it a lot. Okay, so here we see that we have 3 atoms. We have oxygen, carbon, and oxygen. Now, when we add them together, we have this compound. Notice that if you want to know which one goes in the center, the least electron negative will go in the center. Notice that in here, you're going to have carbon, and you're going to have, if you only have one, if you have carbon in the center, and if you only put one bond with oxygen, you have notice that in this case, we have 1, 2, 3, 4, 5 leftovers, which is not okay because now carbon doesn't have the octet. So in order for carbon and oxygen to have the octet, we convert this into, into a double bond. We convert it into a double bond. So maybe I can draw it better. Let me see. Okay, so I give you CO2, carbon, and oxygen. Notice how carbon is going to have 4 electrons, 1, 2, 3, 4. And then oxygen has 6 electrons, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now what we want to do is we want to connect them. So these 2 electrons are going to be shared. Now these 2 electrons are going to be shared. Now count how many electrons are around oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Now carbon has 1, 2, 3, 1, 2, 3, 4, 5, 6. So what we do instead is we share these electrons. And then we're going to share 1 electron of oxygen with that. Now, oxygen, it's going to have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. I think you guys, I kind of cheated in a way. Let me redo this, sorry. Oxygen, 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Carbon 1, 2, 3, and 4. When we combine them, you're gonna combine this ones, and you are going to combine this ones. You're also going to combine that and that. There you go. So I know it looks funny, but it's now every atom has 8 electrons. Notice nitrogen. This is why nitrogen exists as N2. Nitrogen has 5 and 5. If you want them to have both 8, you share through each nitrogen is going to share 3. So notice now oxygen and nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So now they are both happy because they have that octet rule. So you create a double bond or a triple bond. Some characteristics about these bonds: single bonds are longer, but they are also weaker. Double bonds are short and stronger. Triple bonds are even shorter and stronger. So your stronger bonds are going to be your triple bonds. Now, when you have two atoms that are identical to each other, such as Cl2 or H2, we are going to see that the energy is equally being distributed because they both equally pulling, since they both have the same electronegativity. Electronegativity, which we covered earlier. So electronegativity is the ability of an atom to be able to attract an electron to itself. But because in here, they both the same, they're equally going to be able to pull. So you're not going to have what is called a dipole, a difference of electronegativity. Now, when there is a difference, when you have a difference of pulling, we call that a bond polarity, which means that they are not equally pulling to each other. One is pulling more, the electrons are not equally being shared. We also have a term called non-covalent polar, which means that the electrons are equally shared. So in this case, we will have Cl2. An example of bond polarity, we will have something like CO, because they're two different and their electronegativities are different, that they're not equally being shared. Polar covalent bonding means that one electron is pulling more than the other. So those are the type of, like this one, they're type of polarities. Now, in order for us to calculate this polarity, whether it's polar or non-polar, we are going to look at electronegativity, which is the ability of an atom to pull a electron towards itself. Notice here, we see the energy on F2. So here's one F and here's one F. They're equally being pulled, those electrons. So we're saying that the dipole moment cancels. Dipole moment is just basically measures the difference of electronegativity. In here, you have fluorine, which fluorine has like a 4.0 electronegativity, and hydrogen has like a 2.1. So what's going to happen is the fluorine is going to be pulling more, and we draw this vector indicating that fluorine is the more electronegative. Same thing with lithium. Here, you notice the lithium and fluorine. You can see fluorine pulling more because they have a, one is more electronegative than the other. So we consider those polar. So once again, here's the formal definition of electronegativity, which is the ability of an atom in a molecule to attract an electron to itself. Here's the trend. You're not gonna necessarily need to know the numbers, but you definitely need to know this trend. Fluorine is going to be the most electronegative. It increases, notice fluorine is 4. It's going to be the most electronegative. And as you go down, it actually decreases in electronegative. You don't necessarily need to know how to calculate the numbers, but it's going to be very useful for us. Notice here, this is the dipole. So the dipole moment is going to be represented with this partial positive, partial negative. When two atoms are unequally shared, we consider that a polar covalent bond. It's unequally shared. Fluorine is more electronegative than hydrogen, so they're not equally being shared. So this bond is considered polar covalent. Covalent because it's between two nonmetals, right? The electrons are going to be pulled more towards fluorine because the fluorine is more electronegative. And this is going to result in a partial charge difference, which we draw it using this sign. Here is some examples. Notice in here we have the difference between HF and HF is 1.9. The difference between, the difference between HI is 0.4. Because HF has a greater difference, it has a greater dipole moment, and that's how we calculate the dipole moment, which means this is more polar than HI because the difference is larger than the one for HI. Now, this dipole moment that I was telling you is calculated by the charge and the distance, but we're not going to be calculating it. We just want to make sure that you kind of be able to see whether it's polar or non-polar. But this dipole moment is going to happen when you have two different atoms of opposite charges that are separated by a certain distance, and we are going to represent it with a mu. Which pretty much can be calculated. We're not going to be calculated, but I want you to know that the higher the dipole, the more polar something is. This is a chart that can tell you if the difference is 0, you have a pure covalent bond. If the distance is like between 0.4 or something, you have a polar covalent. If the distance is, if the dipole moment is the electronegativity, you have a large dipole moment, you most likely have an ionic compound. So to determine whether something is ionic or covalent, the first thing you want to know is, do it have a metal and a non-metal? If the answer is yes, then you automatically have an ionic compound. If you have a non-metal and a non-metal, you have a covalent compound. There are some exceptions, but we're not going to be getting into that as much. Now, once you have decided whether you have a covalent or an ionic compound, you want to look at the electronegativity differences. You want to calculate those differences to see whether you have a large difference, a large dipole moment, or a small dipole moment. And that will kind of determine whether something is polar or something is non-polar. But there are other tricks on being able to calculate whether something is polar or non-polar, which actually makes things very easier. So that's all introduction. Let's get to the real part of the chapter, the type of questions you're going to be asked. You're going to be given a molecule such as PCl3, and you're going to be asked if you have a covalent bond, you're gonna be asked to draw the Lewis structure, and you're gonna be asked whether this is polar or non-polar, and you're gonna be asked other questions which we're gonna cover in the next chapter. But how do we start? First, you wanna calculate how many electrons you're gonna distribute, which means you need to know the valence electrons. You need to know that phosphorus carries 5 valence electrons, chlorines carry 7. So 3 times 7 is going to be 21, plus 5 is going to be 26 electrons. You have to distribute 26 electrons. That's the first thing that you have to know. That's the first that you have to do. Next thing is, how do you know that phosphorus goes in the center? You want to make sure that all molecules, they like to be symmetrical. So you want to put phosphorus in the center because to make it look symmetrical. In addition, that's not the only reason why you want to put phosphorus in the center. Notice that phosphorus is the least electronegative. So you want to put the atom that is least electronegative. Once you have put it, so you're going to start like this, make it look symmetrical. You want to start distributing your electrons. The first thing you want to do is connect them. So notice that you're going to connect them. Each bond represents 2 electrons. So 2, 4, 6. Now you have 20 valence electrons left. What you are then going to do is complete the octet of all the atoms on the outside. So for example, if you have 20 left, you're gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. You have left 2 electrons. Whatever you have left, it goes in the center atom, and that will give you your final compound. Now, in this case, no multiple bonds are, when they mean multiple bonds, means sometimes you're gonna have to convert to double bond. But in this case, you won't have to do it because notice that your chlorine has 1, 2, 3, 4, 5, 6, 7, 8. So it's happy because it has the active. Phosphorus, it has 1, 2, 3, 4, 5, 6, 7, 8. Phosphorus is also happy, which means that this compound is drawn correctly. Now we have other options. So for example, in here, let's see, I must do it from scratch. Let's say you are giving HCN, and in this case, you want to count how many electrons. You have 1, 4, and you have 5, which means you're going to have to distribute 10 electrons. Now, which one you put in the center? You're going to put carbon. Now, I know that hydrogen is very low electronegative, but hydrogen likes to be terminal. Why is that? Because it can only have one bond attached to it. Hydrogen only likes to have one bond attached to it. So hydrogen likes to be terminal. So we're going to put hydrogen, carbon, and nitrogen. The first thing you want to do is you want to connect them. So that's 2, 4, 5, 6, 7, 8, 9, and 10. Well, if you look at nitrogen has 10 valence electrons, carbon only has 4, and hydrogen has 2. Now hydrogen is happy, and 2, 4. Now notice that we have nitrogen does not have 8, actually has not 10, has 8. I don't know how to count. So nitrogen is also happy, but carbon is not happy. So what we're going to do is we're going to take these 2 electrons and convert them into a bond. We're going to take these 2 electrons and convert them into a bond. Now, nitrogen has 2, 4, 6, 8 valence electrons. Carbon has 8 valence electrons, and hydrogen has 2 valence electrons. Happy, happy, happy. Now I want you to practice and see if you can do it. Remember, hydrogens like to be terminal. The charge means that you're going to add an electron. So for example, on this one, you're going to have nitrogen, which is 5, oxygen, which is 6 times 2, but then it has a negative charge. That means you should be adding 1 electron. A total of 18 electrons, right? 12 plus 5, yep, 18 electrons. So you should be able to distribute 18 electrons. And here you're adding 2 electrons. Here are your answers. Now we're gonna start doing, we're gonna move on and we're actually gonna work on formal charge. So to add it, to do more complicated, we're gonna be calculating the formal charge of each atom that is present in your molecule. Now the way we're gonna calculate formal charge is we're gonna take the valence electrons and we're gonna subtract it by the bonding electrons and multiply it times 1/2. Now, let's look at this compound, which is you have carbon dioxide, and it's in two different structures. So how do we get the 0? We're going to do 6 minus, and it says 1/2 times bonding electrons. And in this case, how many electrons you have bonding? So we can see that the formal charge is going to be 0. And we also can do the same thing with carbon. Carbon, so it's going to be the number of valence electron, which is 4, minus 1/2, and it says of bonding electron, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, minus 8, times minus all non-bonding 0. So 4 minus 4 equals 0. And you do the same thing with this oxygen. Then also notice that you can do the same thing with this oxygen, which you end up with -1. So try to do it by yourself. Now, you have two compounds here. Which of these compounds, which of these structures is preferred? In both structures, the octet rule is being followed. Which brings me to the notes of the formal charges. And the molecule that has all zeros are going to be preferred. A molecular structure in which all formal charges are 0 is preferable. So if you have two structures like the one we did, because this one has all zeros, it's going to be preferred than this one. Not that it's wrong, but it's going to prefer this one. If the Lewis dot structure must have a 0 formal charge, a non-zero formal charge, the arrangement with the smallest non-zero formal charge is preferred. So let me give you an example. Here you have 3 formal charges. So we already know that this has all 0, so this is preferred. But if you only had these 2 formal charges, which one would it be preferable? That one, because it has the smallest formal charge. Then it says Lewis structures are preferred when the adjacent formal charges are 0 or the opposite sign. Then the last one is when we must choose among several Lewis structures with similar distributions of formal charges, the structure with the negative formal charge on the more electronegative charge atom is preferable. So let's give you an example of that. Here we have 3 different compounds. Now, this one automatically we can say that we can remove it, right? Because it has a -2. Now, out of these ones, they both carry a 0, 0, 0, 0, -1. Which one is preferred? Well, which one is more electronegative? Nitrogen or sulfur? The one with the most electronegative, the one that is more electronegative, will be preferable. So in this case, this one will dominate because nitrogen is more electronegative than sulfur. So this is the structure that will be preferred. So that's now we determine the formal charges here. Once you determine the formal charges using the equation, you would generate, why is it flipping? Here are the formal charges. Which one will be preferred? I apologize, but my puppy is a pain in my butt. He thinks he can do whatever he wants. Anyways, I promise we can review this. Once you have determined the formal charge of the compound, you're going to realize that we can automatically ignore the first one because you have a -2. And if you have to choose between something that has a -2 and a -1, you want to make sure that you choose the one with the -1. Now, form C, so this is A, B, and C, has a negative charge on the oxygen, which oxygen has an electronegative of 3.5, and nitrogen has an electronegative of 3.0. So if we have to choose, C will be the best form because that negative charge is being put on the atom that is more electronegative. Here are some practice problems where you need to determine, so you need to draw the compound and you need to identify the formal charge of each. So I'll give you the answers, but make sure you guys know how to draw them correctly. And I would prefer that you do the experiment first before watching the lecture. Here are the answers. Here's another question. This one is easier because they draw it for you. And you want to calculate the formal charge for each of the atoms. And here's the answer. Now I'm going to stop here because my puppy's too energetic, and then I'll continue, but this should get you enough to get you started. Really, Max? Such a... I want to introduce a new topic, which is resonance. And resonance is pretty much this idea that you can rearrange the structure. And basically what you are doing is you are switching the position of the electrons. And in our case, we'll be switching the position of a double bond. For example, if you look at the example below, here we have a double bond on the right side, and here we have a double bond on the left side. So that double bond is being alternated. In reality, neither of these structures is going to be are going to be real. What happens is we are actually going to have a hybrid. And the way we're going to draw this hybrid, it's going to be a hybrid. Sorry, let me try to draw it. And we pretty much, instead what we're going to do is to do this. And then we're going to do this dashes, which indicates that the double bond can be alternated. So as you can see, a hybrid is a mixture in reality. You're going to have a mixture of both structures. So for example, here we have ozone, 3 oxygens. That double bond can exist on both sides. And the way we actually draw it should be in the form of a bend. And the double-headed arrow indicates that it's a resonance. So you want to make sure you put the double-headed arrow. And that will be the resonance. Now there are some rules of this resonance. One of the rules for resonance structure is when you switch those electrons, whatever you switch it, you should have the same connectivity. So resonance structures must have the same connectivity. So for example, when we did this, oops, notice when I'm switching it to the same oxygen, sulfur to oxygen. If I had something like this we cannot switch it, because if I switch this double bond, now it will be sulfur to nitrogen. So it's not the same connectivity. So therefore resonance does not exist. Resonance structures must have the same number of electrons. So if in one form you have 20 electrons, on the second form, you must also have 20 electrons. Second row elements have a maximum of 8 electrons. So here's something that I mentioned, that I did not mention. Any elements that are on the third row or below can have what is called the expanded octet rule, which means they are happy with more than 8 electrons. Formal charges must be total the same. So if in one form the formal charge is 0, the other form the formal charge must also be 0. So let's go through an example. First, you always want to draw the Lewis-Daszak structure in order to maximize the octets, trying to give everybody the octet. So in here, what we did is we have a double bond, but all of them have an octet. So when we write resonance, notice that this double bond can alternate to moving it here, or we can also move it here. So either you can have 3 resonance structures, and it will just be alternating. We also have here sulfuric acid. Notice that in this case, we only have 2 resonance structures. You cannot move the double bond here because this oxygen that I'm circling is not the same as the other oxygen that's connected to sulfur. This oxygen is being pulled by sulfur and by hydrogen. This oxygen is only being pulled by sulfur. So there's only, the double bond can only be above the 2 oxygens, not the oxygens that are connected to hydrogens. Better structures have fewer formal charges. So basically you want to have formal, if you need to have, whenever you draw the Lewis structure, make sure you have 0 formal charge as much as possible. Better structure has smaller formal charge. We already went over this. Better structures have the negative formal charge on the more electronegative. So we already actually went over these 3 rules. So here's the exceptions on the octet rule that we were discussing. As I mentioned earlier, there are some elements that are going to follow the expanded octet rule, and those are the atoms that are in row 3 or below. Sometimes you're going to have an odd number of electrons, such as in NO. When you have free or unpaired electrons, they tend to be very reactive. They're called free radicals. We also have exceptions to the octet rule, such as boron and aluminum. Boron likes to have 3 bonds, as well as aluminum, which means they're happy with only having 6 electrons around it. So notice here we have, this is boron tetrafluoride. They are going to, you can also exist them in this form, which you can have resonance. Unfortunately, they are not as important, or they're not going to be showing us as much, because boron prefers just to have 3 bonds around it, 6 electrons. so boron doesn't necessarily have to have the octet rule. If you actually give boron 8 electrons, it gives it a negative charge on, basically you will have, you will have a negative charge on the boron and a positive charge on the fluorine. And this, it's not because of the formal charge, we rather have everybody being 0. So this is not going to be preferred. The dominant is going to be the first structure. So keep in mind that the idea is that if you have to give it a negative charge, if you have to have a negative charge, you want to make sure that you put the negative charge on the most electronegative atom that you have. Notice here we have phosphorus. Phosphorus is one of the elements that is in period 3. And period 3 to period 6, they can have more than 8 electrons, more than 4 bonds. They are called hypervalent. Whereas this one has 5 bonds, meaning it has 10 electrons around it. And notice the charges when you have in this case, when phosphorus has 4 electrons around it, notice that the overall charge of this compound is -3. And it actually prefers to have 0. Here is a practice problem for you guys to calculate the formal charge. Here's your answers. Formal charge are, and also make sure you guys do your resonance. The last topic, but not the least, it's going to be talking about bond energies, which pretty much is how much energy is required to break a specific bond or to create new bonds. We actually already talked about this, but we're just gonna give you guys an example on how to calculate. You already know how to do this from the previous chapters, but notice to break a triple bond, C triple bond, you need this much energy. To break a double bond, you need this much energy. To break a single bond, you need that much energy. Because triple bonds are shorter and they're also stronger. The shorter the bond, the stronger the bond. When we are calculating the delta H of the reaction, you want to remember that it's going to be the sum of the bonds broken. And bonds broken is going to be positive because they're endothermic. You have to put in energy. The bonds formed are going to be exothermic. So notice here you are forming bonds. You're breaking bonds, which is endothermic. You're going to have to put in energy, and exothermic while you're forming bonds. So we have an example here. Notice that these are going to be bonds that are being broken, which is this endothermic, and this is that are being formed, which are going to be exothermic. Here's the equation. Notice that you always want to make sure that you draw the Lewis dot structure, so you realize that this is going to be H, so you only have one. This is going to be O. Now in here you have H, O, H. So you have one O bond, but you have two OHs bond, and that counts for this. So exothermic and endothermic, you add both numbers, and that completes the problem. Here's an example for you to try your own. And here's the answer. We'll meet and discuss this chapter along with chapter 7 tomorrow.